Hello, everybody. Thank you for joining us today. You are part of the 300 people worldwide who have registered to view this webcast, powered by Yole Développement and dedicated to GaN and SiC. My name is Camille Verrier, and I am Marketing and Communication Project Manager for Yole Développement. First of all, on behalf of the Yole Group of companies, we wish you a Happy New Year and all the best for 2017. Before we get started with the webcast, I would like to give you some information regarding the logistics. You have the possibility during all the webcasts to submit questions. In order to do so, you simply have to use the box at the bottom of the screen labeled Ask a Question. We will answer as many questions today as time permits, and for the remaining questions, we will make a follow-up via email within a week. Concerning the materials and content, please note that the presentation is already available and downloadable in the materials section at the bottom of the screen too, and you will also receive an email after the webcast and within 24 hours with a link to the recorded session. Today, Yole Développement and System Plus Consulting will share their analysis for you to understand the strategy, business, and technology trends that impact the SiC and gallium nitride power industry. First, let's start with an overview of the GaN and SiC devices for power electronics market, presented by Hong Lin, Market and Technology Analyst at Yole Développement. Hong, please.
Thank you, Camille, for introduction. So today I'm giving an overview of the silicon carbide and gallium nitride devices for the power electronics market. Just for the short introduction, silicon technology has long time dominated the power electronic application. But as the silicon technology approach is limited, wide bandgap devices, in particular silicon carbide and gallium nitride, has emerged on the market. And here is a figure of merit, compare silicon to SiC and gallium nitride. I think more and more people are familiar with this figure now. It shows that the SiC and gallium nitride has better intrinsic properties. SiC has higher thermal conductivity and high electrical field and energy gap, which make them advantageous when for high temperature, high power application. Gallium nitride is the preferred choice for high frequency applications. And this better, also the better intrinsic properties allows for better device performance and also can bring system level benefits such as reduce the cost and the size and the weight of the system and eventually reduce the system cost. So now we are look at the market positioning of the gallium nitride and silicon carbide. So far, silicon carbide devices cover from 600 to 3.3 kV range, and the GaN positioning up to 600 volt range. I think in the coming years there will be a coexisting at the 600 volt and 900 volt range for the silicon carbide and gallium nitride. So in the following, I will talk separately for silicon carbide and gallium nitride market. And let's begin with the silicon carbide. Just a little bit about the history. The first silicon carbide diode was introduced in 2001 by Infineon, as shown on the figure. And in the following years, on 7 and 8 years, there was only 2 players, Infineon and Cree. The situation has changed very quickly since 2009, and so today, if we're looking at the commercial availability of silicon carbide diode, we have here is a product chart that Yole has done based on available data sheets, and we can identify by the year of 2016, 17 players that are offering silicon carbide diode. The most of the diode product is concentrated at 600 volt range and 1.2 kV range. We can see on the list of producers, they are traditional silicon power device players such as Infineon, Toshiba, Fairchild Semiconductor, Fuji Electric. But we also have some pure silicon carbide players such as USCI, Haystar Power. The players are coming from all over the world, from US, from Japan, from Europe, and we also notice in the last 2 years the players from Taiwan and from China. So we also note another devices that is made is MOSFET, and the year 2016 compared to diode products, there are only 4 companies that have commercially available silicon carbide MOSFET, which are Microsemi, ROHM, ST, and Wolfspeed. The good news is there are more players that are developing sampling and plan to release the products in the next 2 years. So we are waiting for more and more supplier of silicon carbide MOSFET. For a moment, most of the silicon carbide products is range at 1.2 kV. Some players will provide 600 volt products, and a little bit for 1.7 kV, and further than 1.7 kV products, the MOSFET has been demonstrated by several companies. And so if we look at the market adoption, we think since after 15 years of introduction, SiC diode today is in a very good position. It has gone through the slope of enlightenment, and it's really forecast to grow. For SiC MOSFET, they have really go through these development based on our feedback, and we will look at the market estimation and forecast in the following slide here. So we have estimated the market in 2016 for the all SiC device, including diode and MOSFET, for a little bit more than $200 million, and the market is forecast to grow to more than $600 million in 5 years' time. So far, the market is still dominated by silicon carbide diode for the much ease integration in the system, but in the future coming years, we are convinced that silicon carbide transistor will have a very quickly growth in the next 2 years with a CAGR of more than 40%. So that's about the SiC market, and now we will have a quick look at the gallium nitride market. So in order to have a better understanding of the GaN power market, Yole and our sister company, Nomade, has done a patent scanning in 2015 concerning the GaN power activity. So about 2,000 patent inventions related to the GaN power electronics have been published worldwide till April 2015. The first patents were published in the mid-90s by silicon power companies, but the real takeoff of patenting activity was observed 10 years later with a first wave of patent publication over the 2005 to 2009 period. And the second wave of patent publication started in 2010 when the first commercial products have emerged on the market. So the existing patent covers the whole value chain from the gallium silicon AP wafers to the power semiconductor device to the packaging module, circuit, and the system. So we think that a lot of companies are working on the GaN power activities. So to have a look at patent assigning, here is a ranking of the company's patent portfolio, and we can see that most of the major silicon power players are present on the list of patent application. We find typical the names such as Infineon, Toshiba, Fairchild, Mitsubishi Electric. So that's about the patent status about GaN power activities. And so if we look at the commercial timeline, the first product was released by IR in 2010, and since then several companies has go into the playground. We find EPC, GaN system, transform. Some companies have stopped their activities in between. So now let's look at GaN products that are available. Here is a product chart of the GaN devices by year 2016. Actually, based on available information and product data sheet. So far, we have 4 companies that have commercial available products. As for silicon carbide MOSFET, there are much more companies in developing or sampling of different type of GaN devices. We estimate in the next 2 years there were about 10 players that were going to the playground. And if we look in the product positioning, it's very interesting to notice that we have a very high concentration of the players at a 600 volt, 650 volt range, while only 1 or 2 players at the lower voltage range. For the technical trend, in the last 2 years, we have noticed that there are more and more players working to offer more integrated solution. We have Navitas, Dialog, and EPC that are proposing monolith solution with either several transistors or with integrated driver and other functions such as current protection. There are also Texas Instruments that propose a system in package solution with integrated driver on the same different as GaN. It seems that there is a clear trend to moving toward a more integrated solution. So now, if we're looking at the market forecast, so far the GaN power device market is still very small, a little bit more than $10 million US. The forecast is very optimistic with a CAGR of more than 80%, and the markets will be more than $250 million US in 5 years' time. So we have looked separately silicon carbide and gallium nitride market. Just to conclude, if we compare the silicon carbide and gallium nitride to a total silicon market, the percentage of the market share is still very small. We are talking about 2% market share compared to silicon. And even in the whole forecast period, the percentage remains very small. But just like a glass of water halfly filled, it depends on how you see the things. We can say, okay, the market is still very small and not interesting. But we can also say, okay, the growth rate of the wide bandgap devices is quite important, and there are huge market potential to grab. So Yole is more in an optimistic position to say that there will be plenty of opportunities for device manufacturers, for passive component manufacturers, for the packaging material suppliers. And the question now is how to accelerate the adoption of these wide bandgap materials. It turns out that I think it's obvious for people that there are a real performance advantage for GaN and for SiC. But there are several limiters for the adoption, such as the cost will be addressed by Elena later. There are reliability issues, but we noticed that there are two consortiums for both silicon carbide and gallium nitride to establish standards for the reliability test. There are problems of integration because these are new devices which is difficult to use. The packaging, the module, the converter, say in the converter we have passive component. We noticed that there are companies that working with passive component suppliers to produce high frequency inductors. There are, just as why I say, there are players that offering more integrated solutions, so to easier for the end users which can use this device more easily. And there are also the question of supplier, whether we have multi-sourcing possibilities. As we show, there are more and more players that coming into the market to offer the devices. There are not only startup companies, but also very big companies with big production capacity. So we are convinced that the wide bandgap device market will to grow in the coming years. So thank you.
Thank you very much, Hong, for this interesting overview. Once again, do not hesitate to ask questions using the Q&A button for the Q&A session at the end of the webcast. Now let's continue with Elena Barbarini. She's Senior Cost Engineer for System Plus Consulting, and she will focus her presentation on technology and cost comparison. Elena, please.
Thank you, Camille, for the introduction. So, yes, as Camille said, I will present you a comparison of different components from silicon and silicon carbide, and then comparison between silicon carbide and gallium nitride. So, my presentation we will focus on mainly two range of voltages. So I will compare silicon transistors and GaN transistors on 600 volt. And then silicon and silicon carbide in 1200 volts. And then I will give you a brief comparison of the 900 volt solutions and what's happened if we compare the three technologies, silicon, silicon carbide, and GaN. So just to start, to understand better the cost comparison, I'll present you the supply chain. So here I show you the three different supply chains from silicon, gallium nitride, and silicon carbide devices. I choose for each of any technology two manufacturers. So we'll see that actually the supply chains are quite different. To what concern the silicon, it's quite planar supply chain. That means that the manufacturer, the sellers, all do everything inside. To what concern the gallium nitride, in our cost analysis, we have to consider that often the design is performed by the vendor, but the epitaxy, the front end, obviously it's a different technology, is done by another company, and the packaging again for another manufacturer. To what concern the silicon carbide, in the past the big supply chain structures was the presence of a manufacturer that do the design, the epitaxy, and front end, and then the packaging was done to someone other. Rome, it's a particular case because with the acquisition of SiC crystal, now it's doing everything inside. So let's start to see the differences of technology and cost of medium power devices, so 600 volt. First of all, to recap, in a super junction MOSFET of 600 volt, we have two main technologies in our components. So the multi-epitaxial structures and the deep trench structures. In the first picture, you see the multi-epi structures by Infineon. So you will see that actually there's a big thick epitaxial layers and many deep implantation. In that case, the latest version of Infineon, it has 11 implantation. And on the right, you will see the structures of the epitaxy of deep trench superjunction MOSFET of Toshiba. So here still you have an epitaxy, and then you have a deep trench structures filled by poly or silicon. So these are the two main structures that we can find on the market. You see the current density are quite similar for the two types of devices. The structures of the MOSFET can be planar or trench. If we go and watch what's happened in gallium nitride transistors, so the competitors, first of all we analyze the transforms GaN. Transforms propose an epitaxy of about 5 micrometers with different layers of gallium nitrides, obviously, and as structures that will change in the time. So here we see the first generation with the gold contacts, but then it has other evolution. The package it's typical of transforms. Opposite to transforms, we can see the structures of GaN systems. So GaN systems propose GaN structures with an epitaxy of 5.3 micrometers and a completely different package. So it's an embedded die packages. In this case, we see also that actually the current density, and you have other information about the device. If we compare the three types of device, so the silicon, the GaN, so the silicon with with the deep trench, the two types of silicon devices and the GaN devices from the technology point of view, here you see the results. Obviously, the gallium nitride devices have better performances at low currents for all the 5 examples that I show you. Then if we compare them from the point of view of cost and device size, here we see the main differences. So first of all, the gallium device are smaller for the same current. So that's imply a bigger current density. The die thickness are quite similar, and but the cost it's obviously different. So why the costs are different? If we analyze the breakdown, here we see that actually for the gallium nitride, the main impacts in the cost up to now, it's the epitaxy. So mainly it's due because the epitaxy is quite new, let's say, technologies. so with lower yield. That's an impact on the final cost. Another reason is that the size of the wafers in the manufacturing process actually is still 150 millimeters, while for the silicon devices the trend is already 200 millimeters wafer. To what concern the front side and back side, the front side is quite similar, while the yield losses are really different. So now let's have a look at 1200 volt devices. First of all, again, we'll see the standard technologies. So the standard technologies in silicium are punch-through, IGBT, and fill-stop trench structures. I took the main, not the only one, but the main technologies that you can find in the market in 1200 volts. I compared these two, and so here you see that actually for the punch-through you have an epitaxy layer that we will see have an impact on the final cost. And for the fill-stop trench, you have the trench structures. If we watch the technologies available on the market to what concern silicon carbide MOSFET, we will see. I decided to show you two main technologies. So the technologies for Cree. Cree presents a planar silicon carbide structures. And over silicon carbide substrate and silicon carbide epitaxy. And ROM presents the latest device of ROM because it's a trench structure. So here you see the two main designs that we can find in silicon carbide MOSFET. So if we compare the four types of the design, so the two IGBTs and the two silicon carbide MOSFET, here again we see a big difference in the current density thanks to the size of the silicon carbide MOSFET that are smaller comparing to the IGBT. And to what concern the cost, again up to now the cost of silicon it's the silicon carbide it's quite high compared to silicium. Then if we try to understand the reason of these differences of cost, in that case we see that actually the main impact, the main reason of the cost is the substrate. In fact, as the silicon carbide substrate is much more expensive than a silicon substrate. And again, the yield it has a big impact on silicon carbide MOSFET and the size of the wafer. Here I compared Cree ROM with the Fuji and XES. So actually I will compare a 100 millimeters wafer for the silicon carbide MOSFET and 150 millimeters wafers for the silicon devices. So let's have a look if I compare all the three devices. So in the 900 volt case, so Cree presented recently a 900 volt SiC MOSFET. As you see, it's a family of components with different currents. We see that the figure it's merit it's really good, and the design it's the same as the 1200 volt silicon carbide MOSFET. So if I compare this with a silicon device and a gallium nitride device as we saw before, here we have the three main cases shown. We see that actually the silicon carbide device is much smaller than the other two. And what concern so yeah, you see the die area that's really an advantage at what concern the silicon carbide. If we compare the cost structures, here we have to make a differentiation. So the first comparison is to what concerns the die. Here we see the comparison of the cost of the die. So for the first one, even if we have an epitaxy in the silicon device is not higher impact. Then if we go for the gallium nitride, the epitaxy has a higher impact in the cost. And to what concerns the silicon carbide, actually the main impact is the substrate. If we consider the final cost of the same devices, but with the add of the packaging, we see actually that to what concerns the gallium nitride devices, the packaging has a really high impact at the end that change completely the final cost of the device. So to conclude my presentation, we will so from the technological point of view, we have no doubt that silicon and silicon carbide provides new performances and bring new challenges in the device and the manufacturers. So up to now, we saw that up to now the market it's quite low because of mainly from our point of view, actually the cost it's still not competitive. But actually we think that there will be an improvement mainly in the yield and an improvement on the manufacturing of the substrates that will bring a reduction of the cost of the device. So thank you.
Thank you very much, Elena, for the information you shared with us. We are now going to wrap up with a Q&A session. We will answer something like 2 maybe questions per speaker, and we will follow up via email on the remaining questions. So Hong, maybe 2 questions for you. The first one would be, what is the driving market of SiC transistors?
Hi, so the driving market for SiC transistor, as what we see today, will be PV inverter in the coming years, and in long run, I think there were a lot of opportunities in the other applications such as chargers. That's all.
Okay, and the same question will be for gallium nitride. What is the driving market for this material?
So far, as we say, the market is very small, and there are a bunch of applications. In the future, we think that the primary application will be power supply and adapters for in the consumer telecom regions. There will also be applications for wireless power, envelope tracking, and a low voltage range.
Okay, thank you very much, Hong. Elena, the first question would be, what are the main cost drivers for silicon carbide and gallium nitride?
Yeah, so to what concerns silicon carbide, we consider the main driver the substrate cost, and connected to that the relatively small wafer size respect to the silicon. And to what concerns the gallium nitride, it's the epitaxy, so actually the cost of the epitaxy and the manufacturing yield.
Okay. Second question, what is the impact of packaging in wide bandgap cost, and what has to be done in terms of packaging?
Yeah, so to what concerns the silicon carbide, we saw in our analysis that actually mainly standard packages are used. So design of the packages, it's really common. So maybe some materials are different in the manufacturing. So this has not so much impact in the final cost. But For the gallium nitride, the packaging are really different. I mean, many different manufacturers present different kind of packaging. So we saw the standard packaging for transform, but with the MOSFET and the resistors inside the packaging. And to what concern gallium. To what concern other packaging, we saw the embedded die packaging. So in that case, the packages has a much more high impact on the final cost. So
okay, perfect. So now the webcast is ending. Within the next 24 hours, you will receive an email that will include the recorded session. Please feel free to share the presentation with your colleagues who will benefit from the information that has been presented today, and find all of our analysis and reports on imacronews.com. Thank you for joining us today. Do not hesitate to contact us if you have additional questions, and you can find your appropriate contact on the last slide of the presentation. Thank you and have a good day.